These are three simple, very simple, two-dimensional particle equilibrium problems. And then then the problems will get harder as we go. But these are super simple ones that illustrate the basic principles. So problem one, we basically have a 50-pound weight. This is in a vertical plane. It's suspended from a ring or a point at point A. There's a cable AB and a cable AC. And we want to find the tensions in the cables AB and AC. First of all, you have to draw a free body diagram of something on which you can write your equations. And so you inspect this and you basically say, well, there's a force that acts along AC, there's a force that acts along AB, and then there's a weight here, and all of those forces intersect at A. And so I'm going to draw a picture of A, and I'm going to represent this cable tension with TAC at a 40-degree angle. I'm going to represent this guy as a TAB acting horizontally, and then this is 50-pound force acting down. So this is a free body diagram of point A. It's super important that you draw a separate free body diagram, or you can draw the forces here on the picture. But please draw a free body diagram. Students sometimes try to skip that step, but as the problems get harder, you're going to confuse yourself if you don't. So by drawing this picture, you're thinking about the geometry of the problem. You're identifying the angles at which these guys act. You're assuming directions in which they act. So we're assuming tension. This guy acts down. And then we're going to write our equilibrium equations based on this free body diagram. And then we'll interpret our answers based on the results. For example, you might have a strut problem that you work, and it turns out the force in the strut might be, and you assume that the strut was pushing, but if that number comes out negative, then you go, oh, that strut is actually pulling, not pushing. So you'll see that as we work on. So be very disciplined in how you draw these free body diagrams. So once we have the free body, we're going to write equations of equilibrium. This is a 2D problem. So I can basically write the sum forces in the x is equal to 0. And I can write the sum forces in the y is equal to 0. Those are my conditions for equilibrium. But now I have a strategy, a sequence in which I want to write these equations. If you look at our free body diagram, if I write the x equation first, TAC has an x component, TAB has an x component, and so I won't get an answer from the x equation. It's a valid equation, but I won't get an answer. So strategically or sequentially, I prefer to write the equations in order so that I always get an answer, if possible. So for this guy, I'm going to write the y equation first. And so I'm going to assume a direction. I'm going to assume upward to be positive. And this is something you should do as well. Draw a free body diagram, declare a direction, and as you write term by term this equation, make sure every term agrees with this sign convention. Sometimes if students don't do this, halfway through the equation, they flip the sign, and then the equation becomes invalid. And so declare for yourself what the direction that you're going to assume positive. And you might say, well, it's obvious, up will always be positive. Well, not necessarily. If you've rotated the coordinate system, then these guys might act in a different direction. Or sometimes, especially in dynamics problems, but sometimes I might take down to be positive. It just might be easier for that particular problem. And so we're not always going to take these up or down. So declare a direction. So once you've declared this, TAB does not have a y component. The y component of TAC is TAC sine 40 minus 50 is equal to 0. So TAC is 77.8 pounds. Once we have this guy, then I can sum forces in the x direction is equal to 0. I declare the direction. I have two components. I have this guy and this guy. The weight does not have an x component. So I'll just go TAC cosine 40 minus TAB is equal to 0. And sub the 77.8 in for there, and you'll get TAB is 59.6 pounds. Very simple problem, something you should be able to work in your sleep. Well, in a sleepy state anyway. Know how to do it. Okay, so this is a little bit harder problem. So now the two cables, see this, one of the things that made this super simple is that this cable was horizontal. And so once you sum forces in the y direction, this guy didn't have a y component, and so that makes it super simple. But if you have two cables, neither of which is vertical or horizontal, then they both have x and y components. But in this case, you can tell by looking at the problem that this guy is symmetrical about a line that passes through A and then passes through your weight. And so if you sum forces in the x direction, taking the right to be positive, I have TAC cosine 35 minus TAB cosine 35 is equal to 0. The cosine 35s cancel, and I basically have proven that this tension is equal to this tension by symmetry. And that's something that you should recognize before as you start a problem. Always take a few minutes and look carefully at the problem and map out your plan of attack. This guy, I already knew we're going to write a y equation, get an unknown, then write an x equation. This guy, you're inspecting it, you're going, okay, these guys are symmetric. Okay, so these guys are equal to one another. And so then you don't even have to write the x equation. And once you say these guys are equal, then you can just sum forces in the y direction. And so I've got 2, I'll take up to be positive. I've got 2 TAC sine 35 minus 80 is equal to 0. So TAC is equal to 40 divided by sine 35, which is 69.7 pounds, which is also equal to TAB. And so, relatively simple problem. Now this is a third problem. This is problem 3. And I have 2 cables coming off at odd angles. This one's at 45 degrees. This one's at a 3/4/5 slope. Now I have a 60 kilogram mass here. And so I need to take the 60 kilograms times 9.81 to get 588.6 newtons is my weight as a force. I'm going to draw my free body diagram on this picture. And so I've got TAC, TAB. I'm going to write my x equation and my y equation. For my x equation, I'll take to the right to be positive. I've got a cosine 45. So cosine of 45 is 0.707. And sine of 45 is 0.707. That's a number that you should have memorized. So cosine and sine of 45 is 0.707, which is square root of 2 over 2. For a 30-degree angle, cosine of 30 is 0.866. Sine of 30 is 0.5. Cosine of 60 is 0.5. Sine of 60 is 0.866. Those are numbers that you should have memorized. But in the x direction, I've got a negative 0.707 TAB plus a 4/5 or 0.8 TAC is equal to 0. In the y direction, I've got TAB sine 45, which is 0.707 TAB, plus 3/5 of TAC, which is 0.6, minus my weight as a force, which is 588.6, is equal to 0. Once you write these equations, you've got a plus and a minus 0.707 in the two equations. So even though it's two equations and two unknowns, you could add these two equations, and these guys cancel. You add these two terms, you get 1.4 TAC, is equal to, we're to 588.6, we'll bring to the right-hand side, is 588.6. So TAC is 420.4 newtons. And then finally, we can take this value and plug it into equation 1 to get TAB is 475.7 newtons. And so this is a full-blown 2x2, but whenever I see a 45 degrees, I know I'm going to have cosines in my x, I'm going to have sines in my y, and I know that these guys will be, as long as they're negative and positive with one another, they'll cancel. Or if you assume a direction that ends up being positive, then you can subtract the two equations. But my point is you don't have to solve a 2x2 if you know what you're doing. So the algebra is relatively simple. I'll stop this video here and then I'll work some more problems in another video.